Yeah, good morning. Good morning to everyone. This is Srinivasri from EC Department, Geetam University, Bangalore campus. Today, I'm going to explain about control root locus concept of in control system subject. So, yeah, let me explain what I'm going to discuss in this video. Uh, that is, first I will introduce what is the concept of root locus and why it is required. Then I'll explain what is the angle and magnitude condition. Then I will go to the construction of root locus of the given system with an example. So uh, see in this figure, this is a small example of the feedback control system, as you know already. And here the forward system, so is the transfer forward system transfer function is k by s plus 1, and the unity feedback is applied to this closed loop system. Therefore g of s here, this forward gain is called the open loop gain, or simply the open loop transfer function, that is indicated by g of s. So it is k by s plus 1. Therefore, if you find the transfer function of the closed loop system by after applying the unity feedback, we have the overall system transfer function C of s by R of s is equal to G of s by 1 plus G of s as the formula of the closed loop control system. It gives k by s plus 1 plus k. Yeah, after getting this closed loop transfer function, if you want to know the stability of the system, the main important thing is to know what is the pole location on the S-plane. If you know already, based on the pole locations, we can find the stability of the system. If the poles of the system are lying on the left side of the S-plane, we'll say that the system is stable. If it is lying on the right side, then it is unstable. And if it is lying on the imaginary line, we'll say it is marginally stable. Therefore, for a system to discuss about the stability, pole locations are the path of the roots or poles is very, very important. Therefore, if you want to know the pole locations of a given system, of this system k by s plus 1 plus k, what we need to do is we have to vary the k gain value from 0 to infinity. Then the pole location is the pole location is calculated, and we'll know the path of the poles. If the poles are lying on the left side only, then we'll say for k value from 0 to infinity, the system is stable. But no system will be stable for any value of k, that is from k is equal to 0 to infinity. Therefore, there is a limitation for the k value to be the stable, to make the system stable. We'll find by changing the k value from 0 to infinity, what is the range of the k value, such that we can design a system to be stable. For this, a simple process to know the pole locations for different k value is change the k value from 0 to infinity and know the pole location by calculating the system. From this system, we know that pole location is minus 1 minus k. Therefore, if substitute k value from different k values and find the pole values in this, and place these pole values on the S plane, then we'll get all, since all poles are real values and negative values, all the poles are lying on the right side of the S plane. Therefore, we'll say that for k value from 0 to infinity, the value is negative only. Pole value is negative. Therefore, the system is stable for all values of k greater than 0. But this is a simple thing. This may not be the case for all the systems. So we'll see what is the difficulty for the higher order systems. Before going to that, let me give a small quiz. Please, the participant, attend the quiz as displaying on the screen. Yeah, thank you for participating in the quiz. Let me continue. What is the root locus? For the higher order system, we'll generally prefer the root locus concept. What is meant by root locus? It's the root locus is a path of the roots of the characteristic equation. That is nothing but the pole locations of the closed loop system. If we know the path of the poles, then we will say we'll easily find out what is the key range for the system to be stable. How to sketch the root locus? If it is a simple transfer function like the previous example, it's very easy to calculate the pole values for different k values from 0 to infinity or 0 to some higher range. But if you take a large transfer function, a complex transfer function like this, how to find the pole locations? It's very difficult for the higher order system. Therefore, we'll construct the root locus to study the different values of k at the range of k, and how the system is stable, and what are the conditions to make the system stable. So to analyze the stability of the closed loop control system, we have to plot the root locus. And the root locus concept or method is developed by W.R. Evans to find the root locus and the roots path of the roots of characteristic equation and plotting for different system parameters. Then the roots corresponding to a particular value is located and on the S plane for the resultant graph. Then what are the advantages of root locus? The advantage of the root locus compared to the previous methods like RH criteria and simple the k pole values calculation for different k values is it is applied for the higher order systems and to predict the effect of locations for different gain values, that is k values, and you can also find the effect of the overall system stability by adding open loop pole or open loop zeros. What is angle magnitude condition? Before going to the root locus, it should satisfy the angle and magnitude condition. So let me explain what is meant by angle and magnitude condition. See, we are going to calculate the stability of discuss the stability of the closed loop system. So for the closed loop system transfer function, since it is the function of S, the characteristic equation has the roots of complex terms. So g of x and h of x is equal to minus 1. Since it is complex, we can represent this in terms of magnitude and angle like this. So g of s, h of s angle is plus or minus 180 degrees into 2k plus 1, where k is equal to 1, 2, 3 and so on. Even you can apply 0, so we'll get plus or minus, I mean odd multiples of plus or minus 180 degrees, and the magnitude is equal to 1. So to to apply the root locus method, the poles, the terms of the system should satisfy this angle magnitude condition. If these angle magnitude conditions are not satisfied, then there is no root locus exist on the S plane. So how to construct this root locus? The first step in the root locus construction is to locate the poles, open loop poles and zeros on the S plane. For example, you take this system, and here the open loop system is k by s into s plus 1 into s plus 2. We have placed the poles. Since no zeros are here, we place only the zeros on the complex plane, that is s plane. So the first pole here is s is equal to 0, so s is equal to 0 is placed here. Then second pole is s is equal to minus 1, so minus 1 is placed here. And third pole is minus 2, so minus 2 is pole is placed here. And the angle is, since there are no numerator terms, the denominator terms are complex, therefore the angle is nothing but minus of the first term, minus of the second term, minus of the third term. And the second step of the construction of root locus is to determine the root locus on the real axis. To find the root locus on the real axis, we have a method, that is, assume the random point on the root locus or test point on the root locus at different positions. Then we'll decide the root locus existed by testing the angle and magnitude condition. Suppose if you take the test sample at rightmost side of all the poles, then the angle of all the terms, angle of s is equal to angle of s is equal to 0, because the test point is lying on the real axis, therefore imaginary part is equal to 0. So when this is having only the real part, suppose p is equal to 0. P1 is equal to 0.5, so is equal to 0.5, angle of 0.5 is equal to 0 degrees. Here 0.5 plus 1 is a positive number, so its angle is 0 degrees. Here it is 0.5 plus 2, 2.5, angle is equal to 0 degrees. So all these are having angle is equal to 0 degrees, which is not the odd multiple of plus or minus 180 degrees. So angle condition is not satisfied. Therefore, there is no root locus existed till this point, till this first pole. And now we'll take the second test point in between first pole and the second pole. Say suppose 0 minus 0.5. When it is s is equal to minus 0.5, minus 0.5 angle is equal to 180 degrees. But here minus 0.5 plus 1, it is plus 0.5. It is plus 1.5. So these two angles are 0 degrees only because of its positive number. Since it is negative number, we have 180 degrees angle. Therefore, only this pole is satisfying the root angle condition. Therefore, after combining all the angles, we have minus 180, 0, 0. So totally minus 180 degrees, which is the odd multiple of plus or minus 180 degrees. Therefore, there is angle condition is satisfied. There exists a root locus in between these two poles, first and second. Because at any point, test point or in between this, the angle will be minus 180 degrees only. Similar way, if you take the test point at this point, in between second and third pole, we have the angle, overall angle is minus 360 degrees, which is not the odd multiple of plus or minus 180 degrees. Therefore, the root locus doesn't exist in between these two. And finally, if you take the pole, if you take a test point from third pole to infinity, at any point, we'll have the overall angle of minus 360 degrees, therefore, which is not uh, it is minus 3 into minus 180 degrees, which is odd multiple of plus or minus 180 degrees. Therefore, it is satisfying the angle condition. Therefore, the root locus exists from third pole to infinity. Therefore, the root locus exists here and here. Then third point is to find the asymptotes of the root locus. As we already know that the root locus is indicating the path of the roots of the characteristic equation. Therefore, the direction of the path can be estimated by using the straight line, which are nothing but the asymptotes, the direction of the path or curve. And where these asymptotes are intersecting on the real axis is called the centroid. Therefore, we have to find out these asymptotes and centroids. These asymptotes are found by using this formula, plus or minus 180 degrees into 2k plus 1 by n minus 1, where n is the number of poles and m is the number of zeros. For this example, we have, after applying the formula, we have plus or minus 60 degrees, plus or minus 180 degrees, and plus or minus 300 degrees, plus or minus 240 degrees, and so on. But here plus or minus 240 degrees is nothing but plus or minus 60 degrees. Therefore, first three values are enough for drawing the asymptotes on the root locus. And the centroid is calculated by using this formula. Summation of the pole values minus summation of the zeros divided by n minus m. Here the poles are 0, minus 1 and minus 2. There are no zeros. Therefore, the centroid is minus 3 by 3. So it is nothing but minus 1. So if you place the centroid, we'll get here centroid minus 1 point and the asymptotes minus 60, minus 80 and minus 300, that is nothing but plus 60 degrees. After this, we have to find out the breakaway and break-in points. That means why this breakaway break-in are required. Here we have three poles and the root locus exists here and from this pole to here, like this. So every time the root locus path is from a pole, path will start from a pole and ends at 0 or at infinity. Here from this pole, if the root locus starts, it will go here and it should end at either 0 or infinity. Since 0 is not there, it should go to infinity only. And therefore, it will start from here and somewhere it should divert its path and follow this direction and reach to the infinity. Therefore, in the middle of this, at one point, this diversion takes place. That point is nothing but the breakaway point. We'll see how to calculate the breakaway point. The breakaway point is calculated by deriving this equation dk by ds is equal to 0. How to get this dk by ds? We have the characteristic equation from the closed loop transfer function like this, and from this we can calculate k value, and now we can calculate dk by ds. So dk by ds, make it to equal to 0 after derivative. Now we can find the roots of this quadratic equation. We'll get two roots. In these two roots compulsory may not be the breakaway points. Maybe one point is the breakaway or none is the breakaway point. So to test this breakaway point, we have to verify again the root locus, whether this S point is exist in the root locus or not. If we take these 2 points, minus 0.4 and minus 1.5, minus 0.4 is exist here, minus 1.5 exist here. Already we know that in this area only we have the root locus. From again here to infinity we have the root locus. In between these two we don't have root locus. Therefore there is only one breakaway point, that is minus 0.4. So we have breakaway point here and centroid is here and asymptotes. Now the next thing is the root, the path of the root of this root starts from here, divert from this point and follows this route, this direction, asymptote, and reaches to infinity, but somewhere it will touch the imaginary axis. So we have to find this intersecting of imaginary axis. How to find this? For this we have to substitute s is equal j omega in the characteristic equation. Therefore we'll get the equation in terms of k and omega. After comparing the real part and imaginary part on both sides, we'll get both omega and k. We have two solutions here, but k is equal to 0 is not valid because always k should be greater than 0. So this solution is not valid. Therefore the ultimate valid solution is k is equal to 6, where we got omega is equal to plus or minus root 2, that is 1.414. So we have the intersecting point and the imaginary axis at plus or minus j 1.414. So plus is here, minus is here. So the root locus at this root is starting from this root, divert at this breakaway point, follows this at asymptote, touches the imaginary axis at that point and reaches to infinity as k tends to infinity. Similar way, we have one more pole, second pole. This pole, the path starts from this pole and divert at this breakaway point and reaches to this infinity by intersecting the imaginary line at this point. And third pole, the third root locus starts from the third pole and reaches to infinity without any breakaway. And if you simulate this, the software will get like this, and if you draw also you'll get like this. This is about the root locus method, and by this we can analyze easily the k range of where the system will be stable. I hope you understand the concept.